Okay, this is a worked example for the probability functions section. This is a hypothesis testing using the binomial distribution. Okay, so let's have a look. A single observation X is to be taken from a binomial distribution, which is binomial 20 trials probability of P. Now, this question, for starters, is a little bit kind of faulty, really. The process that we use is that we will have a view about the parameters of a distribution. So normally we would say, right, we believe this to be P equals 0.3, a probability of 0.3, and then we'll devise our hypothesis test accordingly. So the very statement here kind of implies a sort of a kind of rather skewed view of how the process works. So you have to be careful about this sort of thing. Really not a great deal once you read on, because it says an observation is used to test this hypothesis. Well, of course, what we do is we have our hypothesis first, and then we do the test. So really, we should have hypothesized that the probability is 0.3 before we start on our test. So so just watch out for things like this. It's meant to throw you, but it demonstrates a little bit of a skewed view of how the process should work. It also says a single observation X is to be taken. Sort of unusual kind of phraseology there, but quite valid. X is the random variable. It's going to be the number of successes in your trials of 20. So that's the random variable that you're using as your test statistic. So let's just have a look a bit further then. Observation is used to test this null hypothesis that the probability is 0.3 against the probability that it's not 0.3. This is going to tell us it's a two-sided test. Using a 5% level of significance, find the critical region for this test. Probability of rejecting either tail should be as close as possible to 2.5%. Now, the thing, of course, with a discrete distribution, such as the binomial, our critical region can only be whole numbers. It can only be, a number of successes, and those numbers don't necessarily correspond to these nice sort of round number percentages that we've got here. So if we have a look, so here's a bit of an idea of the distribution. Now, I've drawn this as a curve. In actual fact, what it is it's a series of bars because they are discrete probabilities, but it just kind of makes it easier to draw, really. So, and it's skewed, of course, with a probability of 0.3. You're going to expect the kind of the peak of this to be shifted over to the left, and that's what I'm trying to sketch there. Okay, so what we've done, I've done some calculations using the class whiz, and this shows us that the probability that the random variable, the number of successes that we experience in our trial, is less than or equal to 2 is going to be 0.0354. Okay, so that's indicating a sort of a tail here with values 0, 1, and 2 in here of this probability. And then at the top end, the probability that the random variable is less than or equal to 10 is 0.9828. So that actually means that the probability that it's greater than 10, 11 up to 20, is going to be 1 minus that value, which is 0.0172. So therefore, really, that defines our critical region. That's as close as we're going to get to 5%. The sum of these two ends is going to be 5%, and these actual values are probably as close as you're going to get. Well, definitely as close to 2.5 as you're going to be able to get. Arguably we can meet one of these criteria, but not. We could get closer to this one at the expense of this one, or we could get closer to this one at the expense of this one. So, that's just the issue that we have with discrete distributions. So our critical values are less than or equal to 2 and greater than 10. We might say greater than or equal to 11. So those are the critical regions. Anything that falls in between, we would just ascribe to being sort of random variation and not really enough evidence to disprove our hypothesis that the probability is 0.3. So the actual significance level of the test is, as we can see here, some of these two is 0.0526, not too far away from 5%, in fact. Okay, we go ahead and do our test. We observe a value of 3. And of course, 3 doesn't sit in our critical regions. So we are concluding there's not enough evidence on this test to disprove within reasonable probability that our parameter p equals 0.3 is incorrect. So we would accept the null hypothesis that the probability is 0.3 because the test statistic is more likely than the critical value. Okay, so that's pretty well it. So just just going back to this first one, just a kind of a warning on these things. Don't be put off by questions which are probably badly put together, as is this one. So anyway, hopefully that has been useful, and thanks for listening.